So now that we've talked about delta HF, what's left? So from day 2, I did 2 things, right? Delta HF, and then what was the other thing? Delta G. So I should figure out what delta G is used for. So let's do that now. Gibbs free energy, delta G. Anyone remember the formula for Gibbs free energy? It's okay if we don't, but I think we should try to put that somewhere.
H minus TS.
Yes, excellent. And H is the?
U plus PV.
Good, but what is it called? Enthalpy.
No.
Right? Excellent. So, what does Gibbs free energy actually tell us? Gibbs free energy tells us whether or not a reaction will happen or continue, and in which direction it will go. So, what are the possibilities? One will be that delta G is positive. One will be when delta G is negative. Sylvan?
What?
I'm going to call this negatives and positives, okay? And the third one will be when delta G is 0 in a reaction. So when delta G is positive, that means that the reaction, in order to reach equilibrium, must go in a backward direction. So that means the reaction will go to the left. When delta G is negative, the reaction will proceed forward to reach equilibrium. So that means the reaction will go to the right. So when delta G is 0, that means the reaction is at equilibrium and nothing further will happen. In this case, your delta G will actually be minus RT log of Kg. And usually what we do is we put a little symbol 0, remember, for standard state. Oh, I should have probably told you guys that before when we were talking about Kg here. The units of Kg. Generally, Kg are dimensionless, but sometimes when units are assigned to them, they are atmospheric pressure to the power delta N, or mole per liter delta N, where delta N are defined as the sum of the moles of product minus the sum of moles of reactant. Okay, another thing I have to tell you is, since I have defined this delta G0, I'm going to tell you what it is. So delta G0 is the Gibbs free energy at standard state. So why is delta G0 important? Now, remember, delta G tells us whether or not a reaction will continue, and it'll tell us what direction it will go. But it doesn't quite tell us whether the reaction is spontaneous or not. So in order to figure out whether the reaction is spontaneous or not, we require delta G0. So in general, when the value of Kg is greater than 1, the reaction is spontaneous. And what do we know about spontaneous reactions? They happen automatically. You don't need to do any additional input of energy or anything like that, right? Once you initiate the reaction, it will continue forever. Well, not forever, but it will continue on its own. How do I write that? Okay. Spontaneous reactions do not require additional energy input once the reactants are mixed and the reaction is initiated. Now, delta G that we knew, defined as delta H minus T delta S from here, tells us about the direction of the reaction. But it doesn't tell us if the reaction is spontaneous or not. So how do we find whether the reaction is spontaneous or not? So in order to do that, we have to do delta G0. And delta G0 can be defined as delta H0 minus T delta S0. So I'm going to tell you two different things. And delta H0, sorry, delta HG0 no, delta G0 is the Gibbs free energy at standard state. It is the maximum energy available from any chemical reaction. So how did this give us that equation? So two forces that derive chemical reactions always are enthalpy, which is the change in internal energy, potential energy of atoms. And number two, the entropy of the system. Always increases. So these are the two forces. Enthalpy is given by delta H0, and entropy is given by delta S0. So I combine these two things to give me that expression over here. Okay, generally, if delta G0 is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. Gets a little bit more complicated than just this simple picture.